Yeah, my name's Robbie. I'm going to be talking about some tools for debugging certain kinds of JuMP models with some graph algorithms. I'll skip this introduction. And to narrow the scope a little bit, I'm not going to be talking about debugging all types of models that JuMP can support, or even debugging all the types of problems that can occur in the types of models that I do debug. But what I am going to talk about is debugging the constraints of nonlinear optimization problems. And I'm talking here specifically about scalar constraints of scalar variables, basically just algebraic expressions, equality, inequality constraints. And these constraints can have many different types of problems. You can write them incorrectly. They give you wrong answers. They can be incorrectly infeasible. They can be singular, which is the type of problem that I'm going to talk about here. And singularity in constraints of nonlinear optimization problems is a problem because it can violate constraint qualifications that nonlinear local solvers rely on, which at best slows down convergence and at worst leads to problems that just don't converge at all. And this work is all motivated by a situation where you kind of write out all the equations that you'd like to include in your optimization problem. You code them all up, you choose your data, you write an objective function, finalize everything, send it to a solver, and it doesn't converge, doesn't give you an answer. And when this happens, you don't necessarily have a lot of information that tells you exactly what went wrong. And this, I mean, this probably never happens to like any of you guys, but for me, this happens all the time, like, you know, almost every time I write a model. So to be a little more specific, an example of a model I've worked with is let's just say a countercurrent gas-solid flow reactor where we have a chemical reaction happening. This reactor is modeled as a one-dimensional PDE with one spatial dimension and a time dimension. I threw this together in infinite opt and put some initial conditions, some boundary conditions. This is just this system of equality constraints in some optimization problem, let's say, but I'll just be looking at the constraints here. So if you code this up, like I did, send it to our favorite solver, favorite nonlinear solver, IPOpt, and try to solve, in this case, just a square simulation problem. This is coded up exactly as I wrote it on the previous slide. You get this dreaded too few degrees of freedom error from IPOpt, and then the fallback strategy is for JuMP to relax all of the fixed variables and try to solve it again. And when this happens, it converges infeasible. So this is something that happens to me all the time. And it's not necessarily the most informative error in the world. IPOpt's not telling us exactly what we need to do to go and fix our model. So when I was a grad student and this was happening to me all the time, I kind of solicited some advice from other grad students, from my advisor, et cetera. And kind of these are some of the best practices that I came up with at the time, which were to probably the most helpful thing I was told was to try a simpler version of the model. That can really help. Other than that, I was left to look through all of the constraints and expressions that I had written and try and figure out which one had the bug in it. And if you think about this is kind of a quadratic algorithm. So every time you make a mistake when writing your model, you have to go back through all of the constraints that you've written already and figure out which one has the typo or the faulty assumption or whatever. Reconsider all of your assumptions, comment out half your variables and constraints, see if that helps you narrow down where the problem is. But for the types of errors that I'm talking about here, so singularities and degree of freedom issues, there's actually a systematic approach that you can take, which is to compute a maximum matching of your variables and constraints. And that can tell you where a structural singularity is or why you have a different number of degrees of freedom than you expect. And so this is a maximum matching on the bipartite graph of variables and constraints. So we have one set of nodes for variables, one set of nodes for constraints, and we can perform a matching. The maximum matching tells us if the maximum matching doesn't include every variable or constraint, then the the system is, the Jacobian of the system is guaranteed to be ranked efficient. And the type of rank deficiency that really causes problems for optimization solvers is when you have a row rank deficiency in the constraint Jacobian. And so this is helpful for identifying when there's a problem, but it's not always the most useful thing for diagnosing the source of the problem, because the result of a maximum matching is not unique in this little two equation, 3 variable system that I wrote. We could match X or Z to the first equation. Maximum matching, not unique. So the decomposition that actually is unique and provides us with concrete information that we can use to diagnose the source of a modeling error is the Dulmage-Mendelsohn decomposition, which tells us, it splits our system into 3 subsets, which give us all the possible variables and constraints that could be unmatched in any maximum matching. And so these are the system of variables and constraints that are under-constrained, well-constrained, and over-constrained. And looking at these systems, I found in experience with a couple different problems has really helped me to be able to diagnose the source of singularities and degree of freedom errors. So if I throw that reactor model that I showed you earlier at the Dulmage-Mendelsohn decomposition, what do we see? So what I'm showing you here is the incidence matrix on the left, and then I'm highlighting the over-constrained system in the middle. And so the fact that we have an over-constrained system means that the Jacobian is guaranteed to be singular. The over-constrained system contains these variables that I'm showing right here. I'm not going to list them out one by one, but it also contains the initial and boundary conditions, and this equation in the bottom right of the slide. So I'm not going to go through this in excruciating detail, but what we've done here is overspecified our corner conditions in this PDE. So we have initial conditions, we have boundary conditions, and if we happen to apply both of them at the corners, we overconstrain our system and get an error that we can diagnose pretty easily once we have this information. So the solution is just to relax either the initial or boundary conditions at these corners, and then we can reapply the algorithm. We see that we no longer have an overconstrained subsystem. We can send the problem back to IPOpt and actually get a solution this time. This is kind of an algorithm that I throw at all of the nonlinear optimization problems I ever solve. Really is pretty cheap and gives really useful information. It would be really nice to have it in kind of a general package, which let's just forget about that for now. Right, if we had such a package, it might have a syntax that looks something like this. You construct an incidence graph, perform some useful algorithms on the incidence graph, and then get back some data in terms of your JuMP variables and constraints. Would be nice to have. Right, so what I'm going to do next with this is there's a couple other algorithms that we'd like to implement. We'd like to use some of the decompositions as maybe pre-processing steps for some solvers. Maybe we'll integrate with Plasmo, integrate with MOI for some derivatives, and yeah, that's what we're doing. Thanks, guys.